Okay, thank you very much. Thanks very much for the introduction, and it's a great pleasure to be back here at the IAS. So today I want to talk about an application of bifurcation theory to geometric analysis, and it has to do with Q-curvature, and I'll introduce all of these objects as we go along the first hour. So I'll begin by saying a couple of things about what I mean by bifurcation and what's the main tool that's going to detect bifurcation. So the setting that I want to use for bifurcation theory, and this is like a 5-minute crash course in bifurcation theory, will be the following. So we start with a one-parameter family of functionals, so I'll call these ft, from x to r. X is some, perhaps a Hilbert manifold or Hilbert space. So this is a one-parameter family of functionals. And we're interested in critical points of these functionals. And we begin with a curve of critical points that is somehow available from the symmetries of the problem, or somehow it's easily achievable. So they're easily available solutions. So I'll call this the trivial branch of solutions. So trivial branch of solutions. By solutions, I mean solutions to the Euler-Lagrange equation. So dft xt is equal to 0. So it's nothing but a curve of critical points, right? So and somehow it should be somewhat trivial. They should be easy to find solutions. And then perhaps the picture looks something like this. We have here our space X. Here's the parameter t. And for each t, we have a critical point, xt. And we would like to see whether somewhere, perhaps over there, there's a special point xt star where bifurcation occurs, in the sense that there's other solutions that converge to xt star, which are not part of the family we knew from before. Right? So we'll say that, so definition, we say that bifurcation occurs at xt star if there exists a sequence, I'll call them xn, of other critical points, so xn converging to xt star, and a sequence of corresponding tn's converging to t star. So these are the corresponding values down here, such that, well, xn is a critical point for df tn, but they are new ones. So they are different from the ones we have in the family, right? And, well, of course, this is stating this in this way is precisely negating the conclusion of the implicit function theorem, right? I'm saying that in any neighborhood of this point, there's other solutions that are not in the graph, right? So, so this is precisely saying that the implicit function theorem must fail at this point. And of course, that means that the hypothesis cannot possibly be satisfied, right? So it follows that a necessary condition for that, so a necessary condition for bifurcation to occur is that that's a degenerate critical point, right? So xt star is degenerate, meaning that the second variation is not invertible. So by the way, I'll fix some notation here. I generally want to write the second variation in terms of an operator, so I'll just say that at xt star, if we plug in two vectors here, phi, phi, this will be represented by some Jacobi operator at t star. So, so I'm fixing some kind of background inner product. If the manifold is Hilbert, you have a natural one. If sometimes it's not, you might play with regularities there a little bit, and I don't want to get too technical on that, but let's just assume there's some kind of L2 pairing, say, and you're working with smooth functions, but you still do an L2 pairing there. And then this operator here has non-trivial kernel, right? So what I mean there is that jt star has non-trivial kernel, right? So, so that's definitely a necessary condition for bifurcation to occur, but it's not sufficient. And then a lot of work went into trying to understand when can you detect bifurcation by, for example, measuring topological invariance right before and right after where you suspect there's bifurcation, and trying to establish that things actually bifurcate. So that can be done. So to state or there's a classical sufficient condition for bifurcation in terms of, for example, the Morse index in this case, since the problem is variational. So in terms of the Morse index of xt, which is just counting how many negative eigenvalues. So I'll write spec jt for the spectrum of this operator, the Jacobi operator, and we'll count how many eigenvalues are below 0. Right? So there's a classical condition in terms of the Morse index, and that in the context that I want to use later, this goes back to Krasnoselski. So this is a result of Krasnoselski. And it states that if this operator, if the Jacobi operators are Fredholm of index 0, or Fredholm, it's actually representing a symmetric guy. So if it's Fredholm, it's automatically of index 0 in this case, but so of index 0. And if there exist 2 points, let's say A and B, such that XA and XB. Yep, please.
So just to make sure I'm following the notation.
Oh, yeah.
So if you postulate that from the very beginning you have a curve of solution, isn't it always the case that there's a non-trivial Jacobi field independently of bifurcation or non-bifurcation?
Okay. So I'm slightly lying. What I want to do here is that I want to let this vary as well. Okay. So I'm slightly simplifying things, and I'm calling just the space X. But is that answering your question?
So then are you assuming they are all subspaces or Banach submanifolds in a larger space?
I'm not sure what you're saying about.
Well, for instance,
yeah.
So I wonder whether to give a meaning, for instance, to the L2 pairing there, you're postulating the XTs.
They're all inside,
to live inside something.
Yeah, I'll give you an example in just a minute where X is going to be like W12 and they all sit inside L2, for example. Yeah. So I'll give you a very concrete example, and I hope I don't offend anyone's intelligence by giving a very silly sort of Calc 2 example in just a few minutes. But
you see the point, right?
But
I'm thinking about the horizontal variations, right?
Yes.
Along the curve.
Yeah. So so F varies with T. So you were saying if there were a family of critical points for the same functional, that would define a Jacobi degeneracy for the Jacobi vector, right? For the Jacobi operator. But the functional also changes with T. Yes. Yeah. So maybe I'll write it in a bit. But okay. So but either way, so these 2 points, for example, could be perhaps over here we have A, and over there we have B, and we would like to compare the Morse indices at these 2 points. So if there exists A and B such that XA and XB, we want to ask them that they are non-degenerate. And the Morse index at XA is different from the Morse index at XB, then there must exist some T star between A and B, a bifurcation instant. Okay, so that detects bifurcation. Jumps in the Morse index detect bifurcation, right? Right, so, okay, but by the way, of course, it detects at least the presence of a degenerate critical point, right? If you measure the Morse index here and it's something, you measure the Morse index there, it's something else, either you gained or lost some negative eigenvalues, so at least something crossed 0, at least there's a degenerate critical point, actually there's more, there's bifurcation in that case, okay? But let me perhaps give a very concrete example. So there's a classical example as well, which appears in engineering, actually, which is buckling of certain structures. So buckling of structures under compressive stress. So the situation here is that you have, for example, a rod or something, and you start putting some amount of load on that rod. So I'll draw it horizontally here. So perhaps we have a bar over there, and it has length L. And we start putting some amount of weight on one side and start compressing this thing. At some point, the structure will fail and will buckle, right? So, so eventually, what could happen if the load is too heavy, then this thing is going to actually buckle and look something like that, right? So to have some parameters here, maybe I'll call this x, and I'll say x is between 0 and L. And I'll call w of x the deflection at x. So the deflection at x. So how far away you are from the original state of your system. So here, w is identically 0, while here we have positive deflection somewhere, right? And in engineering, it's an important question when how much load does the structure hold? How much weight can we put on it? And this actually was modeled by Euler. So Euler observed that this is prescribed by the following equation. So the second derivative of w multiplied by some elasticity constant. So this E is just an elasticity constant. And that depends on the material, presumably, plus p times w itself is equal to 0, where p here denotes the load. So p is how much weight we're putting on this structure. Okay? So these are two constants that show up there. And of course, if we're looking at, for example, pinned boundary conditions, so if we're assuming that, that we have pinned endpoints, then w of 0 is going to be 0, w of L is also going to be 0, and then we know how to write what are all the solutions to this equation, of course. So, so in general, we would have something like a linear combination of sines and cosines of lambda x, where lambda is the square root of p over e. But if we have that w of 0 is 0, the cosine term cannot possibly be there, right? So we have just a sine term. And w of L being 0 gives you some condition on lambda, right? So we know that lambda has to be of the form n pi over L for some integer n, possibly including 0, right? So, so of course, just the trivial solution corresponds to lambda equals 0. But you see that if lambda is very small, if lambda here, which is that p over e, square root of that, if this is smaller than the first eigenvalue, the first non-zero eigenvalue, then only the trivial solution exists, right? So only w0 identically 0 is a solution to that problem, which means that the structure does not buckle, right? So as soon as you get to p, if p is bigger or equal than, well, the first time this is going to happen is e times pi over L squared, right? As soon as you get to this level, then you get other solutions. So this is what you call the critical load that structure can hold, right? As soon as you pass that, the structure might actually buckle. So actually, if you pass n of these eigenvalues, then there are n non-trivial solutions. So of course, these are just wn. Maybe I'll write wj of x is sine of j pi x over L for every j between 0 and n. Right? So you start gaining these other solutions. Right. And then you can draw a little diagram, perhaps, of how they look like. So we have the trivial branch at 0. So this, you can think of this as the energy level, right? So here I'm writing an energy that I have not yet written down, I guess, but the energy level of these solutions. There's the trivial solution, which is always at the level 0. So this would be W0. And then at these instants where an eigenvalue becomes larger than one of these multiples of pi, for example, the first one is e pi over L squared. The second one is e to pi over L squared, and so on. At all these instants, there's another branch of solutions that is born, Right? So if you go further down the road, then you get arbitrarily many solutions. Right? So this would be W1, W2, W3, and so on. So these would be the bifurcating branches. In this case, they're actually continuous branches of solutions. And that is actually reflected by the fact that these eigenvalues are simple eigenvalues. With the boundary conditions, they're simple eigenvalues. Right, so I want to see these solutions also coming from the variational structure. So variationally, you could write a function, and I'll use p as the parameter since this is the parameter that we're dealing with in this case. So the functional here would be defined on W12, and it's just integrating that equation, right? So we just write f of p would be the integral, let's put a half here, integral of e w prime squared minus p w squared dx, right? So, right, so if we use that energy, then we can see the critical points are solutions to this equation, of course, and then so critical points are exactly solutions to the equation we have at hand after you integrate by parts. And then typically what happens is that, well, this equation that we're going to be dealing with is going to be nonlinear, right? In this case, it's a very simple problem, so you already have a linear equation. So you linearize again, you just get the same thing. But in the applications that I'm about to discuss, this should be some kind of nonlinear PDE that has a geometric meaning, right? But in this case, it's linear already. So when you linearize, again, the Jacobi operator is just this. So it's going to be minus e times the second derivative with respect to x minus p. And because of that, we can compute the Morse index quite easily, the Morse index of the trivial solution. So the game that I want to play here is, suppose that you could not solve this equation. Suppose you didn't see these other solutions. You just have 0. And you compute the Morse index of 0. And you would see that this Morse index is exactly how many eigenvalues of this operator are negative. And that's exactly counting how many natural numbers are below that threshold, are such that e times j pi over l squared minus p is negative. Okay? So this number jumps each time you cross one of these values, right? Which means that the Morse index jumps precisely when you get these new solutions. Right? So this number jumps at each pj equals e j pi over l squared. Right? So you get bifurcation in that way. Okay. So we want to sort of emulate this in a geometric context and have a trivial family of solutions that somehow comes from symmetries, for example, and then analyze their stability and see if they become more and more unstable, then you get more and more solutions that are perhaps harder to find directly. So here we could find all the solutions to that equation, but in general you might expect that the equations you're dealing with are too complicated to have a complete analysis like that, and bifurcation will give you new solutions. Okay, so maybe I should then move on to the second part of my title, which is Q-curvature. So I'll tell you a little bit about that. So Qcurvature and Panit's operator. So I want to fix a manifold of dimension at least 5. The case of dimension 3 and 4 is very different. So in this talk, we'll focus on manifolds of dimension at least 5. And then you can write the curvature operator of this manifold, decomposes as a product of the Schouten tensor with the metric plus the Weyl tensor. So this A here is the Schouten tensor. So to have formulas for it, and don't want to scale this in the wrong way. So this would be 1 over n minus 2 times Ricci minus scalar over 2n minus 1 times the metric. And Q-curvature is defined in terms of the allometric symmetric polynomials in the eigenvalues of this operator. So, so the Q-curvature of our manifold can be written in the following way. So this is something that that was defined by Branson in the 80s, 85, I believe. So Q is going to be Laplacian of the first allometric symmetric polynomial in the eigenvalues of AG minus plus rather 4 sigma 2 of AG plus n minus 4 over 2 times sigma 1 of AG squared. Okay. So it's a funny way to cook up some curvature quantity, but it behaves very nicely under conformal transformations. That's kind of the point of this quantity. Just to give you an idea of what this looks like, if you write this out in terms of its components, the leading term here is something like the Laplacian of the scalar curvature, right, which is traced there, minus 2 over n minus 2 squared times the square norm of Ricci, plus this rather horrific fraction times the square of the scalar curvature. Okay? But the point, rather than what the coefficients are, is that it's a linear combination of Laplace of scalar curvature, square norm of Ricci, and square of scalar curvature. So it's a fourth order quantity in the metric. And the reason why this quantity is so special is that it behaves very nicely with respect to conformal changes. So we can write down a transformation law that somehow mimics what happens for a scalar curvature using the conformal Laplacian. And the role played by the conformal Laplacian in this case is played by the Paniz's operator. So the Paniz's operator is this fourth order operator given by the square of the Laplacian plus there's a divergence of 4 AG minus n minus 2 times sigma 1 of AG times the metric applied to nabla u dot. So it's the divergence of this whole thing in that slot, plus n minus 4 over 2 times the Q-curvature of the metric times the function u. So, okay. So Q-curvature shows up as the 0th order term there. So note that if we just plug in 1 into the Paniz's operator up to that multiple, we just get the value of the Q-curvature, right? And as advertised, the reason for caring about this is that there's a beautiful conformally covariant relation here, which is given by the following. So if we change the metric, let's say we start with the metric G0 and we change it by a conformal factor u to the power 4 over n minus 4, then the Paniz's operator of the resulting metric applied to some function phi is equal to u to the minus n plus 4 over n minus 4 times the Paniz's operator of the original metric applied to the function phi. Okay? Which in particular gives you how the Q-curvature changes. Right? So plugging in 1, you get that the Q-curvature of G is 2 over n minus 4 times u to the minus n plus 4 over n minus 4 times the Paniz's operator of G0 applied to the conformal factor u. And I'm missing a u here, I apologize. Yeah, this should be u times 4. Sorry. So if you set phi to be 1, you get this. Okay. Right, so I just want to compare this with what happens with scalar curvature, right? So compare with the conformal Laplacian. So the conformal Laplacian LG This is 4 times n minus 1 over n minus 2 times the Laplacian of G plus the scalar curvature. This operator, it's conventional to use a different power here. So in this case, G would be u to the 4 over n minus 2 times G0. And then the conformal Laplacian satisfies an analogous transformation law.
What are different signs there, right?
Well, my Laplacian is positive, yeah.
Okay.
Yeah, I am a geometer, I'm not an analyst, I apologize. I'm a geometer giving an analysis talk, but this is positive, yeah. So, so this is u to the minus n plus 2 over n minus 2 times L G0 of u phi, right? Which in particular gives you the transformation law for a scalar curvature, right? So the scalar curvature of G is u to the minus n plus 2 over n minus 2 times the conformal Laplacian applied to u. So, so in some sense, my motivation as a geometer to deal with Q-curvature, despite the name curvature, this to me is more of a quantity related to the curvature operator that behaves very nicely with respect to conformal transformations in terms of a fourth order operator, right? So if you want to deal with the second order operator, of course, this is really what's conformally covariant. And the theory that Branson and Panitz and others developed, in some sense, shows that this is the only natural fourth order conformally covariant operator on functions. Okay, so so there's a parallel to the story of the Yamabe problem in this case of Q-curvature. So in the Yamabe problem, you try to find a conformal deformation u that makes scalar curvature constant, and then the sort of the version for Q-curvature would be finding a conformal deformation u that makes this quantity here constant. And in terms of why one should care about optimizing Q, there's also the same sort of story for the Yamabe problem, where you're dealing with a critical Sobolev exponent, so you have non-compactness of a certain embedding, and the Yamabe invariant has to do with the optimal Sobolev constant. Here you also have something related to the optimal Sobolev constant, but with an embedding of W22 rather than W12 inside a proper LP space. Okay, so right, so perhaps I should then continue this parallel and say what this comparison with the Yamabe problem gives. So, so perhaps I can do this side by side. So I'll discuss the Q-curvature problem, the constant Q-curvature problem, in comparison with the Yamabe problem. Right, so in both cases, given the setup that you can see on the upper board, these correspond to some kind of nonlinear eigenvalue problem for these operators. Here, the Panitz operator. So here you would like to solve p g0 of u equals some constant times u to that funny exponent n plus 4 over n minus 4. And this constant up to a multiple will be the Q-curvature of your desired metric. So n minus 4 over 2 times Q-curvature of G. While here, we want to solve conformal Laplacian of u equals lambda times u to the n plus 2 over n minus 2. Here, lambda is just a scalar curvature of your conformal deformation. Right, so if you succeed in finding a positive function that satisfies this, then you have yourself a conformal deformation that achieves constant curvature. Right? Okay, and both have a nice variational structure. So here, G, which when I'm talking about the Q-curvature problem, I always convention that G is that u to the 4 over n minus 4 times G0. This G has constant Q-curvature if and only if, well, and with the volume normalization. So, and volume 1, if and only if it is a critical point, or if and only if U is a critical point of the total Q-curvature. So this functional Q that goes from the conformal class of G0 to R, that to each metric G gives you the total Q-curvature of G. So with respect to the volume form of G itself. And this, you can rewrite this in terms of U. So I guess I'm using it here being either G or U. If you write it in terms of U, this is just U times the Panet's operator applied to U, dvg0. Right, so by G0 sub 1 here, I mean unit volume metrics conformal to G0. And of course, that's parallel to the story in the Yamabe problem where G has constant scalar curvature and volume 1. If and only if it is critical for the total scalar curvature. Right? So maybe I'll write S for total scalar curvature in the unit volume metrics conformal to G0. So here S of G is the integral of scalar curvature of G with respect to the volume form, which is the same thing as integrating U times the conformal Laplacian of U times the volume form of G0. Right, so there's a complete parallel story there. And there's an advantage in this case, which is that when you have solutions, you can use the maximum principle, and somehow positivity of U, you need U to be positive to define a metric, right? That turns out to not be such a huge problem here, but it is a serious problem here, because you cannot generally guarantee that the solutions you get will be positive. But there's a well-developed existence result also in the Q-curvature problem, which even given some very recent progress, it's almost as good as what the complete solution is in the case of the Yamabe problem. Right? So there's a well-developed theory of existence there as well. So what I want to talk about is not the existence part. Rather, I want to focus on the multiplicity part and use bifurcation to produce many examples of metrics with constant Q-curvature. And to do that, since I already have this parallel going on, I will maybe I'll try to squeeze in here the Jacobi operators. So for future reference, I'll try to squeeze in here the Jacobi operators from the second variation of these functionals. So the Jacobi operator here, there's a multiple of Q that I always forget. So it's n plus 4 over 4. So the Jacobi operator of the metric G, so G is a critical point. Then the Jacobi operator applied to some function psi is 1/2 of the Panet's operator, psi minus n plus 4 over 4 times the Q-curvature of G times psi. And I guess since I'm writing both, I might as well write the Jacobi operator here. So at a metric G applied to psi, this is just a Laplacian, again positive, minus scalar curvature over dimension -1 times psi. Right? So the Morse index is just counting how many eigenvalues of the Panet's operator are below this potential. Right? So it's again some kind of fourth order Schrodinger type operator. Just like here, the Morse index is computed using the eigenvalues of the Laplacian. There, you're replacing the Laplacian by this sort of Laplacian square plus lower order terms that make the operator conformally covariant. Okay. Okay. So as I was saying, the hope is to produce non-uniqueness results for metrics with constant Q-curvature, and there were a few results known in very special cases, but somehow there's a lot of non-uniqueness that happens in the Yamabe case. So as soon as you're talking about conformal classes with positive Yamabe invariant, there's a wealth of non-uniqueness results. and in many different topological types. And somehow the problem is there's even perturbation results that say that you can deform a conformal class by an arbitrarily small amount and achieve arbitrarily many solutions to that conformal class if you're doing deformations in C0. Right? So there's a lot of non-uniqueness that happens here. And perhaps one should expect some of these to pass on to that scenario as well. So that's what we wanted to understand. But there's also some new non-uniqueness results that occur there in the Qcurvature situation that are not that don't have parallels in the Yamabe world. So I want to discuss a little bit of these, and I'll state sort of a detection tool for bifurcation, and then I'll discuss some consequences of them. So to state this sort of criterion, I need to define something about horizontal Einstein submersions. So suppose we have a Riemannian submersion. A Riemannian submersion, let's say fiber F, total space M with a metric G, and base B with metric GB. So I'll call the submersion map pi. And I'll say a submersion is horizontally Einstein if the Ricci tensor in the total space decomposes as a sum of a horizontal Ricci and vertical Ricci, of course, when restricted to the corresponding horizontal spaces. And the horizontal Ricci is some number kappa times the pullback of the metric in the base, right? Okay. So, okay. So then, for submersions that satisfy this property, we have a criterion. Perhaps I'll state this here just so that I can point at it later. Of course, notice that this notion is different from just requesting that the base is Einstein, right? I mean, the Ricci tensor there. If this is a product, it's the same thing, but the bundle could be non-trivial, right? So you have some other contributions from the fundamental tensors of the bundle as well. But to state this recognition criterion for bifurcations, and this, by the way, is joint work with Paolo Piccione and Yannick Sire from last year. So suppose we have one of these submersions. So suppose F goes to mg, goes to b, gb, is a horizontally Einstein Riemannian submersion. And I also want to assume that the fibers are minimal. So with minimal fibers. And not only that, I'll include a parameter here. I'll say pi t gt is a one parameter family of these things. Okay? So we have a one parameter family of horizontally Einstein Riemannian submersions with minimal fibers. And let's assume that, so for now this is an assumption, and then in all the applications we'll get this assumption from the geometry. But since I don't want to talk about that right now, let's just assume that the scalar curvature of these metrics in the total space, as well as the Q-curvature, they're both constant. So such that these things are constant for each t. Okay?
Can you actually construct that?
Yes. Yeah, so for example, the Hopf bundles, for example, will work. But yes, so if we have these assumptions, then let's define two quantities here. Let's say alpha t. Alpha t is just some number which doesn't really matter much, but some number times the scalar curvature. So this number here times the scalar curvature of the metric gt minus 2 over n minus 2 times the horizontally Einstein constant of the submergence. So it's just important that these two quantities appear. The coefficients are not very important. And beta is minus 2 times the Q-curvature of the metric GT. So in terms of these two quantities, we can detect bifurcation in the following way. If there's an eigenvalue of the Laplacian, if there's lambda in the spectrum of the Laplacian of the base, so I'm talking about the base manifold B, and I'm talking about the Laplacian, not the Panitz operator, since that would be much harder to compute. But if there's some lambda in the eigenvalues of the base, such that half of lambda squared plus alpha t lambda plus beta t is equal to 0, and if you linearize this in t, so alpha t star prime lambda plus beta t star prime is not equal to 0. So here, by alpha t star prime, I just mean ddt of alpha t at t equal to star, and similarly for beta. Right? Then this t star, sorry, there should be a star here as well. Then this t star is a bifurcation instant. So then metrics with constant Q-curvature bifurcate from GT star. Okay? Not always. And the point is that many times it's easy to recognize when they don't. So that's a very nice observation. These bifurcating solutions, these bifurcating metrics, do not have constant scalar curvature when this lambda is not equal to the scalar curvature divided by dimension minus 1, right? By the implicit function theorem, for example. So, so of course I'm saying there's our family GT, there's GT star over there, and there's bifurcation for the constant Q-curvature problem. And I'm saying if you're sufficiently close, then these bifurcating solutions only have constant Q-curvature without actually having constant scalar curvature, provided you're close enough. But that's relevant because as much as I'm sure there's a local deformation result that allows you to make this into a constant nearby without having constant scalar curvature, I don't really know a clean way to build a global example of a metric with constant Q-curvature that does not have constant scalar curvature already. It seems like if you're assuming symmetries or if you're doing something, then they're always going to have constant scalar curvature anyways. But this gives you very concrete ways to build global examples with constant Q-curvature and without constant scalar curvature. So perhaps also to address Karen's question, I'll give some concrete examples. So there's a family of nice examples that perhaps I can include over here. So perhaps I'll write this as a corollary. And the statement is that there are infinitely many bifurcations or infinitely bifurcating branches of metrics with constant Q-curvature but without constant scalar curvature. On the following manifolds. So you can take any of the Hopf bundles. For example, you can take S1 goes to S2 Q plus 1 goes to CPQ. You can take S3 going to 4Q plus 3 going to the quaternionic projective space. You can take a circle quotient of this, which is a CP1 bundle of CP2Q plus 1 that also fibers over the quaternionic projective space. Or you could take the 7-sphere bundle over the 8-sphere, which gives the 15-sphere. And if you take any of these Hopf bundles, and then you take the round metric or the Fubini-Studi metric, and you rescale the fiber by t, so I'll put a t here in front of the fiber, just meaning I rescale all the vertical directions by t. Well, this builds you a family GT of metrics on each of these spaces. These are the Berger metrics, for example, in the sphere. And these metrics, they do satisfy all the assumptions that I mentioned in that theorem. And you could do two things. You could send t to 0, and you can send t to infinity. And they're very different behaviors. If you send t to 0, or you send t to infinity, then you get infinitely many bifurcations for the constant Q-curvature problem. Well, you don't get in this first case, but you do get as t goes to infinity, provided that Q is at least 6. You get them on the second bundle if Q is anything, if you're collapsing the fibers. And if Q is at least 2, you also get infinitely many bifurcations when you dilate the fibers. In the case of the 15-dimensional sphere, you always get them. And in the case of this complex bundle, you get if Q is at least 2 in this case and 3 for the infinity case. Right, so provided the dimensions are sufficiently high, you get infinitely many bifurcations, both as you collapse the fiber and as you dilate the fiber. And perhaps the more interesting part here about dilating the fiber is that any positive occurrence that you see on this side is very, very different from what you see in the Yamabe problem. So, and that's because these Hopf bundles, when you enlarge the fiber, they become negatively curved. So perhaps I can squeeze that in here. So if you're sending t to infinity, the scalar curvature of these manifolds actually goes to minus infinity. So as t goes to infinity, the scalar curvature of gt goes to minus infinity. So does the Q-curvature, as a matter of fact, in some range. So this happens essentially always, but the Q-curvature goes to minus infinity as well in the following range. So on this first bundle of the 2Q plus 1 dimensional sphere, if Q is between 6 and 9, on the 4Q plus 3 dimensional sphere, only when Q is 1, and on CP 2Q plus 1 when Q is 2. So coincidentally, it's actually the first number where I can actually do this. These metrics develop negative scalar curvature and negative Q-curvature. Sorry, this should be the same number as that. This should be a 3, I'm sorry. So this is 4Q plus 3, so that should be a 2. Sorry, I shifted by 1 somehow. So in the first number here that you see that you can bifurcate as you go to infinity, these quantities also go to minus infinity, which means that you have non-uniqueness on conformal classes where the Yamabe invariant is negative, and also any sorts of generalizations of the Yamabe invariant to Q-curvature. So on conformal classes where Yamabe invariant and Q are negative, which in some sense is reflecting the absence of a maximum principle, because if you have negative Yamabe invariant, you have uniqueness for the Yamabe problem because of the maximum principle. Right? So here that fails. Okay, And as also Lucas pointed out, this also gives you global examples with constant Q-curvature, but without constant scalar curvature in all these manifolds. So I want to state one last corollary, and then we can break, perhaps, for... and so this last corollary is the case of products, which is a little bit simpler. So another corollary is that if we have two Einstein manifolds, so if F and B are Einstein, and with positive Einstein constant, so with positive Einstein constant, then you can form, and I guess dimension at least 3 as well, dimension at least 3, then you can form the product, right? So then the product manifold, B cross F, with metric given by GT, which is just T times the metric on the fiber plus the metric on the base. These manifolds, these product manifolds, they have constant Q-curvature. They're also horizontally Einstein. They satisfy all the hypotheses. And indeed, they bifurcate infinitely many times. For the constant Q-curvature problem, both as t goes to 0 and as t goes to infinity. And the reason for that is that, of course, you can just rescale and interchange fiber and base, right? It projects onto either of them. So you just need to prove that you can shrink the fibers. And indeed, you can shrink the fibers, and they bifurcate, because this criterion is verified infinitely many times. So I'll discuss a little bit of that on how to verify that this criterion implies the two corollaries, and a couple of the ideas back here, and also how it compares with the Yamabe problem after the break. So, all right. So in the second half, I wanted to give a few ideas of what go on into actually this main sort of workhorse result, which is what we use in the applications, in the geometric applications that I mentioned. So I'll give first a parallel in the Yamabe case to this result, and then I'll explain how that can be somehow transplanted to the Q-curvature context and what the difficulties are in doing that. And then the consequences, the corollaries, the geometric corollaries that I mentioned, they involve somehow a symptotic analysis of these coefficients alpha and beta as t goes to 0 or to infinity. And they're rather technical, so I'll skip most of that, but I'll just make some remarks on how the asymptotics of these numbers can be used. So I'll discuss some parallels in the Yamabe case. So a parallel in the Yamabe problem. And these results, I'll try to sort of sum up everything into one statement, but they go back quite a while. So there were results by Kobayashi and Schoen in the 80s, so I guess 85, and Rick Schoen in 89, where they look at the case of products of a sphere with a circle. And if you take the sphere here to be the fiber and the circle to be the base, and you collapse the fiber, they usually write it in terms of expanding the circle, right? But if you rescale and you just collapse the fiber, then you can fit this into the framework that I'm about to discuss. This framework was mostly developed by Levi Lopes Lima, Paulo Piccione, and Michele Zedda a few years ago, so that was 2012. And then in joint work with Paulo, we extended this to a few other geometric contexts shortly after. And then there was a sort of nice sum up of all of these results by Nobuhiko Otoba and Jimmy Petian just a few years ago, So I'll sort of describe their version of the story, which somehow encapsulates all this previous work into a sort of nice framework. So the Otoba-Petian approach is to consider the following situation. You have a Riemann submersion. So suppose, so this I guess is Otoba-Petian. So suppose you have a submersion, and it's a one-parameter family of submersions. So again, you have matrix GT going to the base B. And here's always the dimension of the total space for me. And it's a one-parameter family of submersions for T between T star minus epsilon and T star plus epsilon. T star is our candidate to bifurcation point. So this is a one-parameter family of Riemannian submersions with totally, or rather just minimal fibers, with minimal fibers. And again, such that the scalar curvature of each of the metrics in the total space is constant for ht. So a constant that depends on t. Then, if you have an eigenvalue of the base, so lambda is in the spectrum of the Laplacian of the base, that satisfies equations analogous to the ones that we have over there. So namely, lambda is the scalar curvature of gt star divided by dimension minus 1, and the derivative of the scalar curvature of gt, if you differentiate that with respect to t at t star, you should get something non-zero. Then, if these two conditions are satisfied, then there's bifurcation at t star. So then matrix with constant scalar curvature bifurcate from gt star. Okay, so I'll give a sketch of the, well, it's rather a complete proof of this, just skipping some minor technical details, and then I'll say how that's sort of the key idea in proving this Q-curvature problem as well. So so I'll jump. Let me see. Maybe I'll try to keep these on the board. So I'll jump over here for now. So the proof of that result very heavily relies on the fact that since the fibers are assumed to be minimal, if you have a function on the base, u, let's say, and you lift it to m, then you get a basic function that I'll denote u bar. So u bar is always the lift of u, so that this diagram commutes. And if you compute the Laplacian in m of u bar, that's the same thing as computing the Laplacian in b of u and then lifting that. Right? So in general, the difference of these two is something that has to do with the mean curvature vector of the fibers, but that's 0. Right? So, so these Laplacians commute, which means that the spectrum of the base is contained in the spectrum of the total space. Right? So every eigenvalue from the base is also an eigenvalue of the total space. And that's what we're going to use to try to see changes in the Morse index. Okay, so so more precisely, if you look at the conformal Laplacian, so rather a sort of ghost of the conformal Laplacian, let me say LT. Let LT be the function, the operator on functions on the base, defined in the following way. So it's something that looks like the conformal Laplacian, but just defined on the base. So LT of u is 4 n minus 1 n minus 2 Laplacian in the base of u plus scalar curvature of gt times u. So so n here's the dimension of the total space, of course, it's up there. And the scalar curvature is the scalar curvature upstairs as well. But I'm just taking the Laplacian in the base, right? So this operator is such that when I lift this, I get exactly the conformal Laplacian of the metric gt applied to the lift of u, right? So I'm writing an operator down that on the base that lifts to exactly what the conformal Laplacian is upstairs. So this, perhaps I can write, is the conformal Laplacian on the total space with the metric GT. And notice that solving the Yamabe problem for conformal factors that are constant along the fiber amounts to solving the nonlinear eigenvalue problem for this operator here, right? So we can write that a metric G of the form U bar to the 4 over n minus 2 times GT has constant scalar curvature, maybe constant equal to C, if and only if LT of U is equal to C times U to the appropriate power. But in the Yamabe problem, when this is the dimension of the manifold, that's a critical exponent. Here we're dealing with functions on the base, so the dimension is slower, right? So then this becomes subcritical. That's kind of key in all of this analysis. So n here is the dimension of m, not of b. So this equation is very nice, actually. It enjoys the same variational structure that we were discussing over there, provided that it's adapted to this splitting between horizontal and vertical. Namely, u, a function in the base, satisfies this equation if and only if it is a critical point of the appropriate functional. So a critical point of ft on W12 of the base, given by integrating in the base u times LTU, subject to a volume constraint, right? So subject to the L2 2n over n minus 2 norm of this function should be 1. So if you restrict to the sphere, then critical points are precisely solutions to that equation, and the Morse index is computed as the Morse index of 1, for example. So we're assuming that GT are solutions, GT themselves are solutions. So the Morse index of these metrics, the Morse index of the conformal factor 1, is nothing but how many eigenvalues of the Laplacian of the base. So it's important that here it's the Laplacian which is not changing, are below this number, scalar curvature of GT divided by n minus 1, right? And then each time that condition is satisfied, so each time we have some lambda, which is an eigenvalue of the Laplacian in the base, which is equal to this number, but the derivative here is non-zero, then you have a crossing, right? So if this is positive, you gain an eigenvalue. If it's negative, you lose one. So there's always a non-trivial crossing, provided that these conditions are satisfied. That is to say, this Morse index here jumps whenever the assumptions are satisfied. So jumps at t equals t star because of the assumptions on this potential, right? And well, each time you have a jump in the Morse index, you have bifurcation there by the Krasnostavsky result, for example. Okay, so jumps at t equals t star, hence bifurcation occurs. Okay. All right. So the idea is to try to mimic this this strategy in the Q-curvature case, using the variational setting that we have over there. So I guess I'll have to erase this, but okay. so so the proof of the theorem above in the Q-curvature case will begin in a very similar way. So let's say PT is what the Panitz operator in the total space looks like when restricted to basic functions. So PT acting on smooth functions at the base is given by computing the Laplacian in the base of u, so the bi-Laplacian, so Laplace square of u, plus 2 alpha t Laplace u minus n plus 4 over 4 times beta t u. So alpha t and beta t are these quantities defined above in terms of scalar curvature, horizontal Einstein constant, and Q-curvature. So this operator here is defined in this way such that then when you look at the horizontal lift of this guy, that's exactly what you get by computing the honest Panitz operator of the total space applied to the lift of u. Okay, so this guy is the Panitz operator of the total space applied to a basic function. And perhaps what's kind of lurking in the background, and I'm afraid I didn't say it explicitly, was that this constraint of looking at basic functions is a natural constraint for the geometric variational problem at hand, in the sense that the linearization of the problem is already 0 in the vertical directions to this constraint. So if you have a critical point of a restricted functional, maybe said in a different way, a critical point of the functional happens to lie in the constraint if and only if it's a critical point of the restricted function already. Right? So the restricted functional, in principle, could have more critical points. Right? I mean, it's, if you have a critical point of a restriction, it's not clear that the linearization of the unrestricted functional is 0 in the vertical directions. But in this case, the horizontality constraints, the fact that you're looking at horizontal functions, all these functions, they are already stationary in the vertical directions of this constraint, essentially because the complement to these functions are functions that have 0 average on the fibers. And when you're integrating these things, you end up getting 0. That's sort of what's lurking in the background. That's sort of why defining operators like these will lead you to solutions in the total space as well. So, okay, so this is the Panitz operator on G of GT, and a metric has constant Q-curvature. So G, in this case here, the exponent, again, I have to change the 2 by 4. This metric here has constant Q-curvature, let's say equal to C, if and only if U is a critical point of a functional ft, now defined on the other sublove space on W22 of M, which is given by integrating U times PTU on the base with respect to the volume form of the base. And again, with the volume constraint. So subject to the LP norm, P here is 2n over n minus 4, that LP norm equal to 1. Okay? Right. And because of that, I guess to make it completely analogous with what's written on the other side, I guess I should say this is a nonlinear eigenvalue for PT, right? So PTU is C. There's a dimensional constant always, n minus 4 over 2 times C times U to the n plus 4 over n minus 4. Right, so that's the PDE that you're solving with that functional. Okay, so because of this, we can compute the Morse index of the matrix GT, so that corresponds to the Morse index of the conformal factor 1, as how many eigenvalues of the Jacobi operator of this functional are negative. And the Jacobi operator I had written a few moments ago, I can perhaps rewrite it over here. It's going to be how many eigenvalues of the Jacobi operator for the Q-curvature problem are negative. And the Jacobi operator at the metric G is a combination of the Paniz's operator, so 1/2 of the Paniz's operator minus n plus 4 over 4 times the Q-curvature. And perhaps now you can see why I defined alpha and beta in the way that I have above, because when you compute the Paniz's operator and the Q-curvature for these metrics, given that they're horizontally Einstein, there's a decomposition of the Ricci tensor, and the divergence term that shows up in the Q-curvature. All of these things simplify quite a lot. And you can rewrite this as a polynomial in the Laplacian. So this is really where the magic happens. This is half of the square Laplacian of the base applied to psi plus alpha times the Laplacian of the base applied to psi plus beta times psi. Okay. So that's where I'm using all of these assumptions on the metric. I'm using them to rewrite the Paniz's operator, which is this complicated fourth-order operator, as a quadratic polynomial in the Laplacian. Right? So that makes the spectral analysis a lot easier. Now I know how to compute the eigenvalues of the Laplacian. I just apply this polynomial to them, and I have the operators. This is alpha t. I have the operator, the eigenvalues of this operator as well. And then when the assumptions up here are satisfied, namely when you have a 0 of this equation, but such that the linearization is non-trivial, then the number of negative eigenvalues changes. Right? So then the Morse index jumps. So these conditions are crafted exactly in such way to produce a jump in the Morse index. Right? So this quantity here jumps at t equals t star because of these hypotheses, and hence bifurcation occurs. At t star. Okay? Are there any questions on that? Or? Okay, so then the hope would be to sort of apply this asymptotically, apply this detection tool to deformations that degenerate the manifold somehow. So perhaps you're collapsing the manifold or you're sending diameter to infinity. And because of this qualitative change in the manifold, because you're losing topology, you're losing dimension, or you're sending the diameter off, or you're doing something geometrically non-trivial to the manifold, that should somehow be detected in this invariant. So the idea is to try to use this as a detection tool in these sort of more geometrically meaningful deformations, right? So I'll discuss that a little bit, and that's sort of leading to the geometric applications that I mentioned, for example, in the Hopf bundles, as well as other homogeneous vibrations as well. So let me perhaps erase this. So the situation we want to consider is that of one sort of original Riemannian submersion, right? So fix a Riemannian submersion F mg b gb, and then we want to deform the fibers. We want to rescale the fibers, right? So this is generally called the canonical variation. I guess in Bess's book, it's called the canonical variation of G. It's this family of metrics GT given by rescaling the vertical directions by T and preserving the horizontal directions. So this gives rise to a family of submersions. And it's an elementary exercise in Riemannian geometry that these are again Riemann submersions for each value for each t. And if you started with something that has minimal fibers, the fibers here remain minimal. If they were totally geodesic, they remain totally geodesic. But then you want to see what happens with scalar curvature, Q-curvature, and so on as you're doing this, right? So, so for example, the scalar curvature of this canonical deformation is going to be 1 over t times the scalar curvature of the fiber plus the scalar curvature of the base minus t times the square norm of the A tensor, which is the integrability of the horizontal distribution of that bundle. So you see that if the fiber has positive scalar curvature, when you send t to 0, this quantity goes to infinity, which is what is also lurking in the background of some of the applications. While if you send t to infinity, then as soon as your bundle is non-trivial, if your bundle, actually your bundle here, your manifold is a product of fiber and base, if and only if A is 0, because we're assuming that things have, that the fibers are going to be totally geodesic. So in some sense, this detects how twisted the bundle is. So as soon as you have a non-trivial bundle, as soon as this guy is non-zero, the scalar curvature is going to become very negative if t is large. And there's a similar formula for the Q-curvature, which I'm not going to bother writing down since it's quite horrific. But you can write down the Q-curvature of this canonical deformation in terms of Ricci tensors of both fiber and base. Okay. Okay, and then the game is to try to use that, is to try to craft situations where we can use that in combination with this result we just discussed to produce infinitely many bifurcations. Okay. So so maybe I'll write this as a lemma. If you have a submersion as above, so let's say L, here's the dimension of the fiber. M has dimension n, and then the base, of course, dimension, here's the difference, n minus L. So if this guy is a Riemann submersion, and now I do need to ask that the fibers are totally geodesic, so with totally geodesic fibers. And both fiber and base are Einstein, so Ricci of the base is, let's say, lambda b times the metric of the base. Ricci of the fiber is lambda f times the metric of the fiber. And you have some condition on the A tensor as well. So namely, it has only 2 eigenvalues. So I'll say eta and zeta. Well, these are just real numbers which are eigenvalues of a contraction of A. So there exist 2 numbers such that when you write ax, ay, I guess I should say what this is. This is just writing ax, xi, ay, xi, where xi is a base of the horizontal space here. So I goes from 1 to n minus L. This should be some number zeta times gxy. And similarly on the vertical space, so au, av, this is the sum of g axi u, axi v. U and v here are vertical, x and y are horizontal. So this should be a number times gxy. Under these conditions, then the canonical variation is also going to have constant Q-curvature for every parameter. So so perhaps I'll squeeze that in here. So this formula remains true, of course. That's much more general. But under these conditions in the Riemann submersion, then the canonical variation well, it is horizontally Einstein to begin with, so is horizontally Einstein. You can compute the Einstein constant actually quite easily. It's just the Einstein constant of the base shifted by 2 zeta t. And it has constant scalar curvature. Given by this formula. And also has constant Q-curvature. And again, given by a formula that depends on all of these quantities. Okay? So this is sort of beefing up the analogous result for scalar curvature. Right? If you have a Riemannian submersion and you want to do the canonical variation, and you want to know when does it retain constant scalar curvature for every t, right? Well, you need the fiber and base to have constant scalar curvature. That's actually enough if the bundle, if the fibers are totally geodesic, because this term here is going to have zero derivative in the horizontal directions. So in some sense, this is beefing up this observation that Riemannian submersions with totally geodesic fibers whose fiber and base have constant scalar curvature, they have canonical variations with constant scalar curvature. Beefing that up to Q-curvature requires all of the hypotheses above. Okay, so that's essentially how these hypotheses come out. So you want to compute the Q-curvature of these metrics GT and somehow still get a constant for every t. And of course, these are rather strong hypotheses, but they come out for free if you have group actions in the picture. So I'll do a side note here that should not be frightened by the strength of the hypothesis here. There's many examples that come out from looking at homogeneous bundles. So from homogeneous bundles, where we have 3 Lie groups, H inside K inside G, and then you build the bundle K mod H goes to G mod H goes to G mod K. And if the isotropy of H acts with only 2 irreducibles, one for the vertical space, one for the horizontal space, then essentially all of the above hypotheses are automatically satisfied. Okay, so examples from homogeneous bundles with 2 isotropy with 2 irreducibles for the H action for H isotropy. Maybe write like this. Okay, which is the case, for example, in the hop bundles that I mentioned. Right? So since vertical and horizontal space are going to be irreducible, Schur's lemma essentially tells you that all of these things are constant. The metrics are going to be Einstein. These pairings are also equivariant, so they're also going to be multiples of the identity and so on. Okay. All right. So with this lemma and with this result about bifurcation, you could try to start squeezing and dilating fibers of various bundles and see when they produce non-trivial solutions. Okay. And so you can state, perhaps I'll do this with the same. Right, I'll try to keep the same alpha and beta. So you can state two corollaries. So maybe I'll label this corollary 0 and corollary infinity for sending t to 0 and t to infinity. So you can state the following. If the Einstein constant of the fiber is positive, and some dimensional assumption is satisfied, so either the dimensions between 5 and 8 for the total space, and the fiber has dimension at least 3, or the dimension of the total space is at least 9, and then you can allow 2-dimensional fibers. Well, in these cases, then there are infinitely many bifurcations for the constant Q-curvature problem as t goes to 0. Okay. And okay, so the proof of this result is essentially looking at the asymptotics of alpha and beta. So proof is looking at asymptotic analysis of alpha t and beta t as t goes to 0. You can show that the equations in the theorem that detects bifurcation, namely these two things here, you can show that they're going to be satisfied infinitely often, because we know that the spectrum of the base consists of a sequence that goes off to infinity, and then the hypothesis that we have on alpha and beta end up implying that this equation has infinitely many solutions. That is, there are infinitely many values of t accumulating at 0 for which that is satisfied for some eigenvalue lambda. As lambda gets large, t gets small in this case. Okay, so I'll state this kind of loosely. Gives infinitely many bifurcations, since the spectrum of the base has eigenvalues lambda 1, lambda 2, and so on, going off to infinity, and the corresponding t's, so Tn goes to 0 as lambda n goes to infinity. Okay. Okay. So you're using crucially that the fiber has positive Ricci curvature in this case, because you want the Q curvature to become arbitrarily large. So you're shrinking these fibers, and that's going to contribute in the Q curvature and make the Q curvature go to plus infinity as well. Okay. Then you could try to play a similar game as you rescale the fibers by large numbers instead of small numbers. And that's a little trickier, but still gives you some results. So the corollary as t goes to infinity is the following. So here we need that both of these eigenvalues, zeta and eta, are positive numbers. And not only that, they need to be pinched somehow. So there's some horrible constant that I'm not going to write down, but it's a dimensional constant. So it depends on the dimension of the total space and of the fiber, so n and l, such that if the ratio between these two eigenvalues is above this constant, and the same dimensional assumptions as before, so either 5 is less than n, less than h, and l is at least 3, or you have dimension in the total space at least 9, and then you can allow two-dimensional fibers, or if your dimension is very, very large in the total space, 21, then you can allow one-dimensional fibers. So if the fiber has very small dimension, then you really need large dimension in the total space. But anyways, under any of these conditions, provided that you have this pinching, you get bifurcation as you go to infinity as well. So if this is true, then there are infinitely many bifurcation instants for the constant Qcurvature problem as t goes to infinity. And notice here that I am requesting both of these numbers to be positive, which means that the 8th answer is definitely non-trivial, right? So this second corollary does not apply to products, right? This second corollary, so I'll make a note of that here. This does not apply to the product case, since we need the 8th answer to be non-trivial. And so the corollary that I stated in the first part of the talk about products of Einstein manifolds, it's not coming from here. You really need to use the previous results, the one about collapsing fibers, and then rescale. So switch fiber and base, and shrink the base, so to speak, right? Instead of dilating the fiber. So this analysis here actually does not work for products. Okay, but the proof is in spirit similar. It's also an asymptotic analysis of the coefficients. Okay, so proof is also by asymptotic analysis of these coefficients as t goes to infinity. And as you can perhaps infer from the ugly numbers showing up in the dimensional hypothesis, and this, which I'm really hiding, but it's some rational function of n and l, the analysis here gets somewhat delicate. So essentially you do a Taylor expansion of all these quantities, and you want to know when you're going to get infinitely many bifurcations, but the coefficients depend on all of these parameters. They depend on lambda f, lambda b, on eta, and zeta, and n, and l. And you get some polynomials that really we could not find elementary methods to analyze them. I mean, you actually use some real algebraic geometry results to show that in the ranges defined by these inequalities, you get all the inequalities that you need to get infinitely many bifurcations. So really, there's a lot of sort of ugly technicalities that are happening under the hood here that I'll definitely hide. Right. So rather than discussing those, I'll just perhaps finish by commenting on the scalar curvature of these bifurcating metrics. So note that again, some rather complicated analysis of these coefficients show that the bifurcating metrics above, the bifurcating metrics with constant Q-curvature, given by both of the above corollaries, given by both t going to 0 and t going to infinity, provided, of course, these hypotheses are satisfied, do not have constant scalar curvature. And the reason for that is that observation that we mentioned before, namely that the bifurcation instants happen when some eigenvalue of the base satisfies that quadratic identity that corresponds to the Panitz operator. But you can show that under the hypothesis that we are assuming, these numbers are always going to be different from the scalar curvature of the metrics divided by dimension minus 1. Okay. So because of that, provided that you're sufficiently close in the bifurcating sequence, you don't get constant scalar curvature. Okay. All right. So I think I'll end up early, and I'll finish here, actually. Thank you. Right. Well,
from your condition, I think you don't assume you have a sign.
Yeah, it's kind of no. So I'm not assuming any sign on Q, but indeed in both of these ways of applying the theorem, Q is going to infinity. in absolute value, right? It could be going to minus infinity as well. So I guess to answer your question, no, you can apply this theorem both in the case where Q is positive as well as when Q is negative. You just have that Q has to explode to either positive or minus infinity.
For this question, like you mentioned the example by Shen and
Yeah.
Kobayashi.
Yeah.
I think that is originally for the non-uniqueness of the Yamabe equation. Actually.
Yes.
So, but in Yamabe equation, you know, when you have non-positive Yamabe constant, actually the solution is unique.
That's right.
So, does it mean that in Q-curvature, even if the sign of Q is negative, you still can have?
That's right. Yes. So that's perhaps one of the interesting consequences of this result is that non-uniqueness is also possible when Q is negative and simultaneously Q negative and negative scalar as well. So both the Yamabe invariant is negative and the Q-curvature is negative, arbitrarily negative, it's going to minus infinity, and you still get lots of solutions in these conformal classes. Yeah.
So, not, let's thanks.
Thank you.